Swayam Prabha. Digital India. Educated India.
Welcome to module 8 and lecture 2. In the second lecture of this module, we are going to discuss on evaporation principles and evaporator performance. Actually, in the last lecture, that means in the first lecture of this module 8, where we are discussing on evaporation, in the first lecture we have discussed that how and the different types of evaporators are used for different types of materials, and also we have discussed some important points related to the what kind of solvents we should use, what should be the properties of the solution that is getting evaporated, and depending on the properties, different types of properties of the solution, what kind of precautions should be taken, and all this we have discussed. Now, in this lecture, we are going to discuss on some principles related to evaporation and also that performances of the evaporators. That is what we are going to discuss. To start with, we will discuss first the evaporator capacity and economy. So, these are two important terminologies related to evaporation. What we see, first one is the capacity, evaporator capacity. From the name itself we can see is the vaporization capacity, but it is capacity means the vaporization capacity, but it has got a very specific definition. It says that number of kilogram of water is vaporized per hour is the evaporator capacity. Similarly, there is the terminology is the economy. It says that number of kilograms of water vaporized number of kilograms of water vaporized from all the effects taken together for each kilogram of steam fed to the first effect. So, what is the, let us try to understand. In the very first case is that it is considered the number of kilogram of water evaporated per hour. So, from one particular evaporator we are getting how much amount of the water vapor evaporated per hour. But what about the economy? Economy says that number of kilograms of water vaporized from all the effects. So, we can have not only a single effect, we can have several effects. Now, what is this effect? Effect means it's the unit where that a solution is being fed into, and the heating is being done, and the material is evaporated, and the thick liquor is drained, and the vapor is coming out. The whole process which is being happening in one particular unit, that is called an effect. So, this is in case of evaporator is called an effect. So, a single unit which is complete from all aspects is called an effect. So, there can be such effects together, that means there can be series or parallel combinations, I will discuss in later. There can be some effects together, okay. And this is called feed forward, feed backward, forward feed, backward feed, all these things we will discuss. So, when you have such effects together, then total amount of vapor which is vaporized for feeding 1 kilogram of steam, that is very important. So, how many effects you have in the system, whatever amount of the total is coming out, and that is coming out only for 1 kilogram of steam, and that steam is fed into the first effect. Actually, this is the convention to express the effect with first effect, in which the feed is being the steam is fed into. Okay. So, external steam is fed into that particular effect is called the first effect. Okay. So, now what we can understand is that for a single effect, okay. So, for a single effect we can have the capacity economy to be less than 1, as we understand. For if we have a single effect, the if we put a steam, then what will happen? The amount of vapor produced will be definitely less than the steam. The reason is there will be lot of amount of energy that will be wasted during this process. So, this is called, we will discuss in details in little later about this, that what are the factors that is working on this. And so, this is the reason why it is the economy will be less. So, economy for one effect is nearly 0.8. It is less than 1 definitely, and it is 0.8. So, if number of effects is equal to say 0.8, sorry, if number of effects is equal to n, then total economy will be nearly equal to 0.8 n. So, this is a very gross estimation of the things. Now, why this effect, why it is less? The reason behind is that there are 3 things, as I told you, that when the steam is external steam that is heating, so there will be some heat loss. Okay. Then there will be some amount of that enthalpy of vaporization, or I should say the latent heat of steam at higher temperature is less than that of latent heat is less than that of steam at lower temperature. So, what is happening in case of evaporator, that steam is put in the say cell side, and in the tube side the liquid is there. So, the liquid is being heated. So, the liquid is being boiled. So, the boiling temperature of the temperature of the steam will be definitely higher than the temperature of the boiling liquid in the tube. This is to maintain the heat transfer, and therefore, the latent heat is of the steam, which is at a higher temperature, has to be, that will be definitely at higher pressure. The latent heat amount will be less for 1 kg of the steam. So, though 1 kg of steam is being used, but the amount of heat being supplied to the liquid which is boiling is less, and therefore, this reduces the automatically this reduces this value. And also another point, that there will be a heat loss during this process. Okay. So, therefore, the amount of vapor generated will always be less than the amount of steam that is being used for that. So, therefore, the economy is always less than 1. Okay. And then the ratio of capacity to economy is called steam consumption per hour. Okay. Now, one important aspect related to evaporation is called boiling point elevation. So, I will term it as BPE. We know that boiling point elevation is one definite consequences in case of evaporator. What happens is that as we know the what is the boiling point elevation in a solvent. If we put some amount of solutes, there will be an elevation in the boiling point, that is called boiling point elevation. So, the boiling point will increase Now, in case of solution that is to be evaporated, so what is happening with time, with more amount of solvent is going out, and then what is happening is getting concentrated. Higher the concentration, the boiling point will go on increasing. That is what is called boiling point elevation. And if you see that calculation of the boiling point elevation, so in case of evaporation, that boiling point elevation is quite substantial, and so boiling point elevation calculation is a pretty difficult issue. So, it is very difficult. So, what is used is that During's line is used, During's rule used for boiling point elevation calculation. Now, what is During's rule? During's rule states what it says that boiling point of a solution is of a solution of given concentration is a linear function of boiling point of water. That means, it is like this, that if it is boiling point of water is, and this boiling point of some solution. So, we can have different lines based on concentration of various concentration of solute. We will have different lines, and these lines are called During's lines. During's line. So, this is a linear. So, it is a straight line. So, if we can have a relationship for 2 points, then we can draw a straight line, and then we can go for that interpolation or extrapolation of these lines and get information for various concentration terms. So, that is what is the importance of the During's rule. So, if we say, if we accept the During's rule that that is a linear function. So, if we have for at least 2 concentrations, okay, so the boiling points of water and the corresponding boiling point of the solution, if we know, okay, and then we draw a line, fine. So, this is the boiling point of water, and this boiling point of water will change. This boiling point will change because of the pressure of the system, and then the boiling point of the solution is also known. So, then for 2 is, if it is known, then for other concentration we can easily find out. Similarly, for other pressures we can find out. Similarly, for so just by knowing that linearity relationship, and by knowing some of the experimental data, we can find out the other values by using the During's rule. But During's rule is this works good till moderate range of pressure, and is not satisfactory at higher pressure. Okay. Now, this another point is related to the temperature driving force. In case of evaporation, if you see that for a say long tubes are there, as we have seen in the previously, that say this is the liquid entry and this is the position where liquid vapor mixture lives. Okay, and this is the distance along tube. This is the distance along tube. So, this is the temperature, say boiling point of water, Tw is the boiling point of water. This is the boiling point of water, Tw, and so Tb, this is Tb, and this is also, I am sorry, Tb. So, the boiling point of solution. So, that means Tb minus Tw is the boiling point elevation, but and here or what we can say that this is the temperature of saturation temperature, and it is coming with some higher temperature and is coming down. Okay. So, this is Ts. Now, this is a vapor and this is the liquid. So, this region is for superheated vapor, and this is for subcooling. So, what is happening? We have a tube and the liquid is entering, and then it is boiling, and then vapor liquid mixture is going up and it is leaving the tube. So, this is the length of the tube, and this is the boiling point of water, and this is the boiling point under the pressure condition. Okay, pressure condition of the inside the tube, and this is the boiling point. So, boiling point means that the saturation that it boils when that it meets up with the saturation temperature. Okay, and this Tb is the boiling point of the liquid of the solution at that particular pressure in the tube. But what happens is actually as it goes along the tube, so it happens to be like this, that profile is, there is a profile like this, and there is another profile like this. So, this is say for high velocity, and this is a low velocity case. This is the case A and this is case B, say. So, what is happening actually, this is the boiling point of the liquid, but actual temperature happens to be like this for low velocity situation. What happens in this case? We can understand that when a fluid enters into a tube, it has got a different type of pressures acting on it. The pressure is that vapor chamber pressure, total pressure is equal to vapor chamber pressure plus it has got hydrostatic head plus the frictional head loss. So, at any point it has got this much amount of the total pressure. So, based on that it will boil. Now, what happens is that a fluid once it enters, it does, because the temperature is high, it does not boil at that time. Because the pressure is high, it does not boil. It is boil at this point, at the end of this, when the hydrostatic head is not there. So, it boils at this point, it does not boil at this point, and its temperature rises, and then afterward when it may be that it boils here, and then what is happening, that once it starts boiling, then it further reduces the temperature, the temperature gets reduces, it does not require any further, because it is going upward. So, hydrostatic gas gradually decreases and the boiling temperature reduces. So, initially the temperature is high, it is heated up, it is not boiling, and once it starts boiling, then afterwards its temperature reduces, and that boiling phenomena starts because the velocity is low. It starts somewhere in the middle of the tube, and in this case when the velocity is high, it boils somewhere towards the end of the tube, or may not boil even in the tube at all. So, in that situation, when it does not boil in the tube at all, then it is allowed to flash in the, as I told in the last lecture, it is allowed to flash in the vapor chamber, okay, where it will be at a lower pressure. So, it will be flashing, and then using the flash method you can get the vapor out and the condensate come back. So, it will be the condensate means that is the concentrated product that comes out. Okay. Now, this is what is called the true boiling temperature. So, true temperature difference is a variable one. The temperature difference, this is the temperature of the liquid inside the tube, and this is the temperature of the jacket, that is the steam jacket, it is the outside the tube. Okay. So, this T s minus this temperature should be the true temperature difference, T s minus this temperature should be the true temperature difference in case of any flow, but actual this should be the true or actual temperature difference, but what is being taken is that the boiling temperature under total conditions is being taken as the temperature difference on an average. Okay. So, this is what one important phenomena that one should understand pretty clearly. Now, second point is this is about that boiling point temperature driving force and boiling point elevations with these liquids, and then we will go to that single and multiple effect evaporators. Evaporator. Now, so we have understood that one thing that evaporator means there will be a liquid solution and which will be heated up by a heating medium, which could be normally a condensing steam are used, and what happens in that case is that it is evaporated and the thick liquor comes out. So, when everything happens, it is called a single effect. Now, many a times it need not be a single effect, there can be a multiple effects. So, before I just tell about that, one thing I should say here that superheated vapor comes into this little bit superheated, it is not exactly saturated, little bit of superheated, because if there is some heat loss, so then it will be condensed previously itself. So, it is not allowed, so some amount of superheat is needed, and while it is going out of this heat exchanger, then it is little bit of subcooling is possible. Okay. Now, coming to this, in case of multiple effect evaporators, as we have seen that economy, okay, economy is less. Economy is we have seen that less than 1, that 0.8 around. The reason already I have told, there are two reasons could be. One is called is the latent heat of evaporation, that is high, that value is low at higher temperatures of the steam, and the heat loss in the evaporator from the evaporator to the ambient. That is, these are the two things. In addition to this, there could be another point that for which the economy could be less, is that the feed entering, it need not be at saturation temperature. The feed entering would be maybe a cold feed. So, feed may be at temperature below boiling point. So, then we need to put sensible heat. So, this is a different thing altogether, we need to put some sensible heat for that. So, it depending upon the type of or amount of heating needed, that is sensibility needed for this liquid, that economy will be gradually changing for that. Okay. Now, therefore, there is a provision to have multiple effects. Okay. So, multiple effects means that it depends upon the this definition has come, or the variations have come based on the mode of feed supply. As I already told that it is customary, or it is in general viewed that the evaporator in which the external steam is fed is called the first effect. Okay. Now, depending on the mode of the feed supply. So, one is the steam supply, external steam supply, another is the feed supply. So, depending on the mode of the feed supply, it can be divided into 4 types. Okay. One is called forward feed, then backward feed, then mixed feed, and then we have parallel feed. There are the 4 different types of feeding arrangements are possible. Now, we know that for this kind of situations, that usually if there are single effect, in place of single effect, there are two effects. There can be three effects. There can be more than three effects. So, what we have discussed is that with the help of the three effects, we try to show that what is a forward feed, what is a backward feed, what is the mixed feed, and what is the parallel feed, and what is the situation, and what are the positive and negative points that they should be used, and the advantages and disadvantages one would get. So, if we try to see that forward, this is the example of a forward feed. Now, you see that, so this is steam is given here. So, this is how it is called the first effect, this is the second effect, and this is the third effect. That is the very important thing. And then second point is that the feed is coming, this feed is coming from this region. Okay. It is the first time it is coming, and then it is coming like this. So, there will be some amount of recirculation. So, it is basically a is an example of a typically recirculation evaporator kind of things. So, this feed is coming, it is going down, and then feed is coming, and then here. So, what is happening is that, and also you can see that this is the vapor chamber, and vapor is coming again, this vapor is again in the form of steam. So, if it is a water solution, the vapor is nothing but the steam again. So, this is coming as heating medium, again it is coming as heating medium, and this. So, and this is called this is the separator where we are getting the condensate out, and that vapor goes. So, this is a natural condensation that takes place, and here the thick layer is taken out. Okay. So, that's what that means. It says that in case of forward feed, triple effect, this is a triple effect, three effects are there. Forward feed, what we can see here is that vapor goes from this to this to this. That means what is happening, that the pressure in the first effect, second effect, if the pressure of this effect has to be lower than this, pressure of this effect has to be lower than this, therefore, it will move to this region. So, that should be a maintenance of smaller pressures in the subsequent effects. That is very important. That is for the not only the smooth movement of the vapor. So, what is advantage here is that the steam we are putting only once, but in the multiple evaporator. So, this vapor which is coming out, these are again their energy is used for this evaporation again. Therefore, the economy gets increased. But point over here is that if you see that when we are putting the feed over here, that as pressure is high, the boiling point is high, but here the liquid is of a dilute liquid, and once it is high. So, it is getting concentrated and goes to the other one. So, it is getting concentrated, goes to the other ones. Once it is getting concentrated, means its boiling point increases, as we have seen boiling point elevation. So, if the boiling point elevation is there, so and what we want that its pressure to be reduced. So, it works in the favoring direction. So, boiling point is increased. So, what we have to do is we have to reduce the pressure in any case to get into the boiling point situation, to get it boiled. So, the reduction in pressure in this effect will not only make this thick liquor to boil at a lower temperature, but also allow the vapor to come to this, and similarly this thing happens. Okay. So, similarly, so gradual maintenance, so gradual decrease in the pressure, feed is in the forward direction, moving in the, that means getting concentrated more and more in the forward direction, vapor is also going in the forward direction. This is what is called the forward feed. Okay. Now, what is there is that important point over here, that so using forward feed, economy is increased, okay, and it will be as good as 3 times of the economy of the first one. Okay. And the next part is that second part is that this is called backward feed. What is the difference here? In this case, what is being given is that feed is starting from here. So, feed has started from here. So, this is the recirculation, and then it is going to the previous one, and then it is going to this. But the vapor is moving in the as whatever is direction is given, the vapor is moving in the forward direction, but the feed is moving in the backward direction. That is why. So, mode of feed supply, that is what is being classified as. So, what happened in this case, that that means in the last effect, the temperature is less, because steam pressure is less, temperature is less, but first effect the steam temperature is high. Okay. And in case of backward direction, in the last effect, what happens is that concentration of the feed is also high. That means, a thick liquor is treated at a higher temperature. So, a thick liquor is treated as is heated at a higher temperature. So, the only problem in this case is that possibility of having the damage. So, if it is a heat sensitive material, then there is a possibility of having a damage. If I see in case of the forward feed, that its economy is increased, and we see that there is no intermediate pump is needed. So, there is no pump requirement. So, flow through natural ways, okay, in a gradual decreasing pressure, okay, and that more concentrated liquid is evaporated at lower temperature and lower pressure. So, we can say that it is suitable for heat sensitive material. So, this is for forward feed, but in case of backward feed, whatever we have seen, that we need to have the pumps. So, what I will say here now, in case of backward feed, we need to have pump. So, this will increase the cost, capital cost. Okay. But what happens is that it is good for highly viscous material, and not only that, it is good for high heat transfer coefficient can be obtained. In the subsequent stages. As we understand, because it is because increased flowability. If we see again that as we have here in this effect, it is the thickest material. In the effect 1 is the thickest material is vaporized at highest temperature. Thickest material, highest temperature, okay, in effect 1. In case of backward, so thickest liquor at highest steam temperature. So, because of this reason, what happens is that thick liquor, thick liquor means high viscosity. So, its flowability will be reduced. So, its heat transfer coefficient will be reduced. So, if it is done at higher temperature, so then it will be good heat transfer will be possible. But only thing is that in this case that heat sensitive materials cannot be used, because the thick liquor at high temperature may get damaged. Okay. Now, the next part of this is that when the feed is cold. So, when the feed is cold, if admitted in the first effect of the backward case. So, if we have the cold feed, and if it is admitted here in the backward case, then what will happen? Some amount of this steam will be used as a sensible heat to raise the temperature of this, and then that boiling point here, and this point is the boiling point is less, and so the requirement of sensible heat will be low. As what I was trying to say is that in case of backward feed, suppose the feed is cold. So, in case of forward feed, the feed will be placed over here. In case of backward feed, the feed is placed over here, and if the feed is cold, and we know that to have a boiling in this, because it is a lower temperature, so boiling will be at a lower temperature. So, that means I have to give a less amount of energy for the sensitive, as in the form of sensible heat, for this feed to reach to this boiling point. Whereas, in this case, if the feed was here, that means in case of forward feed, I would have used more amount of sensible heat for raising the temperature of the feed to the boiling point. And therefore, for cold feed, that backward mode is always preferred. So, for when the feed is cold, backward mode is preferred. But backward mode, there is a problem that the pumps are required, and these pumps will add extra to the cost, and the geometry will be little bit complicated, flow geometry will be little bit complicated. And then another point I should say that when the in the other end, when the feed is hot, so going to the similar logic, the forward mode is preferred, because we are not getting this advantage of the forward feed when the feed is hot. Okay? And rather we may sacrifice some amount of vapor, because when the feed is hot, then there would be once if we put over here the feed and it is at a lower pressure, there can be there can be some flash in this region. So, all the vapor may not be used up for the vaporization purpose. So, that be that kind of situation may exist. So, in that case we will be losing. So, if the feed is hot, we should use if the feed is hot, we should use forward mode of heat transport. Okay. Now, coming to the next part, which is called the mixed feed evaporator. So, mixed feed case means that feed is it's becoming very easy, because we have taken triple effect. If there are multiple effect, more than 3 also, we can understand the concept. Concept is that feed is given somewhere in the intermediate, and then it is going to the forward direction like a forward feed, and then from the last effect it goes to the first effect again as a backward mode. Okay. So, if we have more than 3, then this mixed feed arrangement can be, there are many possibilities, permutation and combinations can be used, but in case of triple effect on only one particular combination, that is it is given in the second effect, and then it is going forward and then coming back to the first one. Okay. So, first in the middle and then forward effect and then comes back. So, what is the reason behind this? This is a kind of thing that is happening, like it is becoming an intermediate kind of thing, and what it does, it reduces, or that it compromises between the positive and the negative effects of both forward and backward feed evaporator. For example, less pump requirement, less complicacy, less complex is the piping. Okay. So, these are the positive things, and also we can use we can get that high heat transfer rate as we get for backward mode. Higher heat transfer rate compared to forward mode, but less than the backward mode. Okay. So, this is what is important, and then another method is there that we will see, this is called the parallel feed, and this parallel feeding we can see from here that yes, the feed is given, it's just feed is divided and given to the all the effects at the same time. So, it is a parallel supply of the feed to the steams, to the effects evaporators, and that liquor also, the product is also collected parallelly, separately from different effects it is collected. So, there is almost they are independent of each other except the vapor. So, that means heating arrangement is a interdependent things, and therefore, we are increasing the economy, that this heating arrangement will increase the economy, that is what is the idea. But other things are almost independent, and what happens is this is particularly this parallel feed, this is particularly used for crystallization. For this case it is used. Okay. Now, so this is about the different types of supply, and then if we see, so this is a typical summary of the things, the advantages and the different disadvantages of the forward feed and the backward feed cases. And if we see the from the based on the supply mode, for forward feed it is a simple operation, that is what is important, simple operation, less expensive, no pump requirement, and more concentrated liquor is vaporized at low temperature, and thus good for heat sensitive materials, as I was telling, is good for heat sensitive materials. But backward feed is lower viscosity and higher heat transfer rate in the first effect, and it is lower heat transfer rate in case of in subsequent effects, and steam economy is low in subsequent effect, is the lower heat transfer rate. But in backward inter effect pump is required and more fouling. So, fouling possibility is more in backward, and damage of viscous materials due to high temperature, that is what was told. And for mixed flow cases, mixed feed supply, that takes into account the simplicity of forward and economy of backward feed, and good for highly viscous, and number of pump reduced with respect to backward feed. Okay. And complex piping and instrumentation more expensive, complicated to handle. This is also there. So, pipe complexity is there like your backward feed conditions, but parallel feed is suitable for the crystallizers, and is it has got a better control over the system and complex arrangement pump for each effect. So, yeah, it is very important that we have to drain out this liquid, and then we may have to put pump for each effect. And because this pump for each effect is means because it is being placed to the next another unit, which is called the crystallization unit, and that is to be placed. It is this material, this that means its evaporation is the what should I say, that it is the prior unit operation, a priori unit operation for crystallization. So, with the help of a pump, the material is thick material or thick liquor is being placed or put forward to the crystallizer. Okay. Now, there are two important issues that we should say. One is called heat transfer coefficient. Now, if we see from heat transfer coefficient that in case of evaporator, that how the heat transfer is happening, if we just try to see, there are two things here. One is that tube fluid is getting heated, and cell side there is the steam. There is steam in the cell side, which is mostly a condensing steam, and tube side fluid is heated. So, what happens is the condensing steam has got a very high heat transfer coefficient, heat transfer coefficient. Then another point over here is for condensing steam, almost no scale formation, because there is no solute over there. Apart from corrosion, there is no scale formation over here, but tube fluid large possibility of scaling. So, that is very important, that we should see that scaling or we can say fouling. So, that is the large possibility of scaling or fouling. We should reduce as much as possible this scaling or fouling. Okay. So, time to time cleaning is needed. Cleaning is necessary. Okay. This is very important. The fouling part is very important, because it is a solute and solution is there. So, solute will deposit the scale formation and salting out effect, all these points are there, already we have discussed. Now, many a situation what happens is that liquid in the tube is not allowed to boil. Liquid in the tube is not allowed to boil, it flashes in the vapor chamber. So, and there it gets separated into a thick liquor and a vapor. Okay? Its temperature is raised. So, under that situation we can use correlation like HID by K 0.0278, Reynolds to the power 0.8. It is like Siddhartha correlation like that. Siddhartha kind of correlation is not exactly the Siddhartha relation, and this is the tube diameter, tube inner diameter, tube ID. So, this situation when correlation is used when no boiling, and when there is a boiling, then we have discussed already in convective heat transfer that there are some correlations can be used. When boiling correlations can be used. And one thing, as I said, that the fouling is important, and so fouling changes the overall heat transfer coefficient, and there is a relationship 1 by u naught square is equal to 1 by u c square plus beta into theta. So, this is after fouling, this is clean, beta is equal to your constant for a particular fluid, and theta is equal to time of operation. Theta is equal to time of operation. Okay. And typical UD values, sorry, UO values are for STV, short tube vertical evaporator, it is 752.2500. This value unit is kilocalorie per hour per meter square per degree centigrade. For LTV, long tube vertical and forced circulation, these values are roughly 2000 to 10,000. Unit is same, kilocalorie per hour per meter square per degree centigrade. Then LTV, then for natural circulation, for forced circulation, the value is very high. It would be around for natural circulation it will be less, 1000 to 3000 roughly, same unit. Okay. Agitated film such plate type, they have values something around 1500 to 2700 kilocalorie per hour per meter square per degree centigrade. These are typical ranges of the overall heat transfer coefficient values. And then another thing what I was interested to tell is that enthalpy of solution, this is very important. So, enthalpy of solution is very much needed. Enthalpy of solution is very much needed for calculation. This is required for heat exchanger, or sorry, here in this case evaporator calculations. Okay. And this can be enthalpy of solution can be determined by calorimetry or can be calculated from integral heat of solution. So, integral heat of solution is it is the change in enthalpy of a solution when 1 mole of solute is dissolved in the say N1 moles of solvent at 25 degrees centigrade and 1 atmosphere pressure. Okay. So, the enthalpy of a solution at temperature T relative to the pure solvent and solute, okay, at temperature T naught is Hs, enthalpy of this solution, okay, at temperature T is equal to N1 H1 plus N2 H2 plus N2 into delta Hs2. This N2 is the N1 is the number of moles of 1 stands for solvent moles, 2 stands for solute. So, number of moles of solute N1 and N2 equal to number of moles of solvent and solute, okay, and H1 H2 are enthalpies, okay, molar enthalpies. Of solvent and solute, and delta H S2 is called integral heat of solution of solute at temperature say T, and then Hs also can be written as N2 delta H S2 naught plus N1 plus N2 into S into T minus T naught. Here delta H S2 naught is called integral heat of solution of solute at temperature T naught, or temperature is equal to T naught is equal to 25 degree centigrade, and S is called molar specific heat of solution. Okay, molar specific heat of solution. So, thus this is just to have an idea to get the values of enthalpy of solution from integral enthalpy of heat of solution. We can find out the enthalpy of solution, but actually, or we can find out from the supply data or available data in the literature, we can find out the enthalpy of the solution. So, this is one important aspect regarding the evaporator calculations. Maybe in the next lecture, we will be discussing on the calculation of the evaporators. So, here I will ask you two questions based on my first two lectures. So, what kind of evaporators I should use for case 1, highly heat sensitive material, but moderate viscosity material. So, the answer should be force circulation vertical or falling film or climbing film evaporator. Second case, highly heat sensitive with large viscosity, heat sensitive but large. In that case, the answer would be agitated film or plate type evaporators. So, the third question is third part is that for foaming liquid, but not heat sensitive. Okay. So, naturally the choice would be natural circulation and long tube vertical, that should be used. For foaming liquid, you should use long tube vertical. So, this is about the some idea about the different types of evaporators that should use. Now, this is all about for today's lecture, and in the next lecture I will be discussing, and there will be the final lecture for the evaporation. I will be discussing on the evaporation calculations, okay, for the design, and we will see the calculations for single effect as well as multi effect evaporators, and we will illustrate with some specific problems on this. Thank you very much.